Hello, good evening.
Good evening, sir.
Good evening, sir.
Let me define you one thing first about your assignment. I got only Krishna assignment and no, that's it. And I'm impressed, very impressed about your answering, way of answering. Nabila, no assignment, and no one else has done.
Sir, I submitted the second one.
This radiation one.
Yes.
Okay, let me explain you what was the question, how to answer. The first one was, can thermal radiation pass through vacuum or not? Mazia, any idea?
Sorry, sir.
Can thermal radiation pass through vacuum or not? Thermal radiation is basically electromagnetic in nature, so it may travel through vacuum as well, since it does not require any medium for the propagation. Okay. Next, what is the nature of heat radiation? You'll say electromagnetic behavior. Third, what is the absorptivity of perfectly black body? It will be 1. Since black body behaves as perfectly absorber, so absorptivity will be 1. And the last question was, if a hot body is kept in surrounding which are cooler than the body, then only hot body radiate heat while cooler surrounding do not. Is this particular statement true or false? Nabila?
It is true.
True. I had defined you Prevost hypothesis. Okay. On the basis of which state every object which having temperature greater than 0 Kelvin will emit as well as absorb radiation. Okay. Like in the case of a man standing in front of ice, in the case of man standing in front of fire, both objects radiate their energy according to their body temperature. The net flow will depend upon which one will be at higher temperature. Okay.
Okay, sir.
Okay, Krishna has done right. Raza, any doubt related to this assignment?
No, sir.
Okay. Okay, and I defined you in last class Stephen's law, on the basis of which I have given you these two terms. Now let me define you. Just 1 minute. Next term in this particular chapter is Newton's law of cooling. It simply says when a hot body is placed in any cold surrounding, let's say a hot body at temperature T is placed in cold surrounding. At some temperature T naught. So according to Prevost's hypothesis, you will say this hot body will radiate radiation, and since it having more temperature so it will radiate more. But cold surrounding, since it also have a temperature greater than 0 Kelvin, so it also radiate along this direction, but some lesser amount of radiation like this. So if you have to calculate net flow of radiation in this part, so I've calculated in last class. So according to the Stephen's law, you will say net emissive power will be epsilon times sigma t raised to 4 minus t naught to the power 4. You may write this emissive power as energy per unit area per unit time. So it will be heat per unit area per unit time equals to epsilon sigma t raised to 4 t naught to the power 4. Move a to right side or just keep it as it is. So we have to define this newtons of cooling for very small temperature. Let's say delta T is less than equal to 100 degrees Celsius. Delta T equals to T minus T naught. So put the value of T in term of delta T and T naught in this expression. So you'll get dq divided by dt equals to A times epsilon sigma. In place of T, I have put T naught plus delta T whole to the power 4 minus T naught to the power 4. Mazia, any doubt?
No, sir.
Okay. Now, I have to take out common T naught. For that part, let me multiply it by T naught and divide it by T naught. So on solving or on taking common from both these two parts as T naught, you're left with T naught to the power 4 bracket 1 plus delta T by T naught whole to the power 4 minus T naught to the power 4. I've just taken out T naught from this bracket, and since it having exponential 4, so it will become T naught to the power 4. And this will be also power 4. Now, this part and this part both is same. So we can further take out common from entire term. So you'll get sigma A T naught to the power 4 and left with 1 plus delta T divided by T naught to the power 4 minus 1. Nabila, is it clear?
Yes, sir.
Okay. According to binomial expansion, we can write 1 plus x to the power n equals to 1 plus n times x. So this having exponential 4, using this, we may write this exponential to its coefficient. So it will become dq by dt equals to epsilon a sigma t naught to the power 4 1 plus 4 times delta t by t naught minus 1. So this minus 1 and plus 1 will cancel out. So on solving, you will get epsilon a sigma t naught to the power 4 multiplied by 4 delta t, which is nothing but t minus t naught, divided by t naught. So T naught having 4 power and T naught having 1 power, on solving, you will get dq by dt epsilon a sigma 4 times T naught to the power q bracket T minus T naught. In this part, this dq by dt will define you at what rate this hot body is cooling down or it is radiating its energy. And this expression is temperature of body and temperature of its surrounding. And this to the whole quantity, this entire term is constant. Since epsilon is constant, emissivity, 4 is constant, sigma is Stephen's constant, and T naught, which is temperature of surrounding, so it should be constant. So from this part, you will say the rate of cooling, that is dq by dt, will be directly proportional to temperature of body and temperature of surrounding. Nabila, is it clear?
Yes, sir.
So from this expression, we may write this dq by dt as nothing but rate of heat lost by body is directly proportional to temperature difference of body and surrounding. And this entire term is constant. Minashi, any doubt?
No, sir.
Okay, first write it down.
Done, sir.
Nabila, done?
Done, sir.
Mazia, done?
Yes, sir.
Okay. So according to Newton's law of cooling, let me define its statement. State when a hot body is placed in cold surrounding, the rate of heat lost by the body directly proportional to the temperature difference of body and surrounding. What I have proved above. So we can write related to the above part or related to this statement, rate of cooling of a body, rate of heat lost by the body is proportional to temperature difference between body and surrounding. Rate of heat lost is dq by dt. Remove this proportionality sign by any constant term c. Temperature difference is T minus T naught. Since this heat is being lost, so there will be negative sign. So this particular heat on losing into surrounding will be responsible for changing temperature of that particular body. So we may write dq equals to ms times delta T. that is specific heat. So put this expression in the above part, you will get ms dt divided by dt. Move this negative to side to right side, c times t minus t naught. So from this part, you'll get dt divided by t minus t naught equals to minus c divided by m into s multiplied by dt. So I just move this temperature to left side so that same variable will be one side and rest of the whole contain right side. Is it clear?
Yes, sir.
Now we have to integrate this particular part. So on integrating, 1 by x on integration will give you log x at some initial temperature to some final temperature equals to minus this entire term is some another constant k. Dt on integrating will give you just t. So on solving further, you will get ln upper limit minus ln lower limit is equals to minus of k into t. Move this part to right side. So you'll get ln t final minus t naught equals to minus of k into t plus ln t initial minus t naught. Raza, is it clear?
Yes, sir.
Now, just see this particular term is behaving as y. This is slope and this is any constant intercept. So we may write this expression as y is equals to mx plus c. So it is behaving as straight line. This is y. This is any constant c. This is slope and this is a variable x. So in this part, slope is negative, intercept that is c, which is positive. So let me define a graph related to this expression. So it will be straight line, but with decreasing slope. Log temperature T versus time. Krishna, is it clear?
Yes, sir.
Okay, just write it down to this. This is actual Newton's law of cooling. You will be given this statement, or they will ask you, define Newton's law of cooling and derive its final expression. So you'll start from this part, not the above one. Okay.
Done, sir.
You all have written? Mazia, done?
Yes.
Nabila?
Done, sir.
Let me define you from this part. I think most of you have understand what is going here from this part to this part. We have dt. I have put the value of dq as ms delta t, since this loss of heat is changing temperature of that particular object. So it will be ms delta t in concept of specific heat. So moving this ms to right side, so you'll get c divided by m into s, which is another constant such as k. Next is dt, that is change in temperature. So move this temperature part to left side and time to right side. So you'll get this expression. So it is behaving as 1 by x integration. So integration of 1 by x will be log x, ln natural log, that variable x, from initial temperature to some final temperature. Put the value of t to be first, t final, minus t initial. Move this term to right side. So you'll get expression like this, which is behaving as y equals to mx plus c. Straight line expression with having negative slope and positive intercept. Next expression related to this part will be, suppose for this expression, if you remove this log, there will be exponential function for this part. So it will give you t minus t naught equals to e raised to the power minus k into t. So if you have to calculate t, so it will be e to the power minus k into x plus some t naught, like this. Is it clear?
Yes,
Let
sir.
me define just 1 minute. Suppose you have a to the power x is equals to some natural number n, just as 2 to the power 2 is 4, 2 to the power 3 is 8, and so on. So if you have to calculate x in terms of a and n, so it will be equals to x equals to log to the base a n. So we can say log is nothing but a reverse of its exponential part. So if you have to replace this particular term to this part, So on removing this log, this base a will move to its base of x. So n will be equals to a raised to x. Similarly, in this part, we have ln. ln is log to the base e. So on removing this ln, there will be base e for this particular entire constant term. So it will behave like this expression. Nabila, is it clear?
Yes, sir.
So graph related to this expression will be like this. Change in temperature versus time, it will be exponentially decreasing. So it will be like this. For log, it will be straight line, but for t, only temperature change, it will be exponentially decreasing. Just write it down. Minashi, any doubt?
No, sir.
You all have done?
Yes, sir.
Raza?
Yes, sir.
But for calculation purpose, since log is very difficult to solve, so let me define your shortcut method how to calculate numerical related to this entire part. According to the above relation for this part, ms delta t divided by this, we may write as dt divided by t equals to minus of c divided by m into s, which is some constant, times t minus t naught. So on solving, this numerator dt is change in temperature, so it will be T final minus T initial. Denominator dt is time difference, so it will be T minus 0 minus this entire term is some constant K. This T is termed as average temperature, so it will be Ti plus Tf divided by 2 minus T naught, which is temperature of surrounding. So if you have to remove this negative sign, so just shift this and this. So you'll get T initial minus T final, since the body will have larger temperature initially as compared to its final, divided by T equals to some constant K, T initial plus T final divided by 2 minus T naught. So this will be your final expression for calculation of problem on Newton's law of cooling. Nabila, is it clear?
Yes, sir.
Let me define your problem and how to solve it. It says a body at 60 degrees Celsius is placed in surrounding of 10 degrees Celsius. In 5 minutes, its temperature become 40 degrees Celsius. Find time in which its temperature may fall to 20 degrees Celsius if Newton's law is valid. So in this question, we have temperature of surrounding, that is T naught, 10 degrees Celsius. Temperature of object initially is 60 degrees Celsius, which becomes 40 degrees Celsius in 5 minutes. We have to calculate further time to fall its temperature to 20 degrees Celsius. In first part, time taken is 5 minutes. We have to calculate time for its second interval. First, write it down to this part. Krishna, done?
Yes, sir. Done.
Let me define you how to solve this part. In this segment, we have 60 degrees Celsius to 40 degrees Celsius, first interval, and next 40 degrees Celsius to 20 degrees Celsius, next interval. So break this entire term into two parts. For first part, we have T initial 60 degrees Celsius, T final 40 degrees Celsius. So put these values in the above part and try to find the value of K. Similarly, for second part, T initial will become 40 and T final 20 degrees Celsius. Put this term in the above part and simplify both these two equations to find the value of T. Nabila, is it clear?
Yes, sir.
Try to solve. Try to find the value of K from equation first, put it in second equation, you'll get value of T. Good, Krishna. Let me solve. 60 minus 40, it will be 20. Divide by 5 into 6, 30, 300. K, 60 plus 40, 100. Divide by 2, 50 minus 10, 40. So this part and this part cancel in 2 times. So you'll get K is equals to 1 by 600. Put this term in the second equation. 40 minus 20, 20 divide by T, which we have to calculate. Value of K is 1 by 600. 60 plus 20, 40 plus 20, 60 divide by 2, 30 minus 10, 20. This part cancel out. So you're left with T is equals to 600 second. Divide by 60 to convert into minute, you will get 10 minute or 600 second. Nabila, is it clear?
Yes, sir.
Minashi, any doubt?
No, sir.
Now in this part, let me define you. Initially, we have body at 60 degrees Celsius. So to reach 40 degrees Celsius, it was taking just 5 minutes. And further, to reach 20 degrees Celsius, in this interval, it is taking 10 minutes. So from this part, we can conclude temperature difference of these two parts is also 20 degrees Celsius, and temperature difference of these two parts is also 20 degrees Celsius. So to change the temperature by same amount, it will take longer time at lower temperature, and it will take smaller time when it is at higher temperature. Initially, it was at 60 degrees Celsius. So it was taking just 5 minutes to cool down by 20 degrees Celsius to reach at 40 degrees Celsius. But further, when its temperature was 40 degrees Celsius, it is taking 10 minutes to cool down by same amount, 20 degrees Celsius to reach 20 degrees Celsius. Is it clear?
Yes, sir.
So from this, we may conclude on lowering temperature of body, its rate of cooling down decreases. So to change the temperature of body by same amount, it will take longer time. Raza, is it clear?
Yes, sir.
So at lowering temperature, rate of cooling down of body decreases. So it will take longer time to change temperature by same amount. At lower temperature. So you will be asked, suppose if a body is initially at 100 degrees Celsius, it cools down to 90 degrees Celsius, further to 80 degrees Celsius, and further to 70 degrees Celsius. Let's say time taken is T1, T2, and T3. So what would be relation between T1, T2, T3? So you'll say, since temperature difference between all three segments is same, but since this is initially at 100 degrees Celsius, which is at higher temperature, this is 90 degrees Celsius, which is slightly lower, and this is further lower. So on decreasing temperature or on lowering temperature, the rate of cooling down of a body decreases. So it will take longer time to change by same amount. So we can say T1 will be least than T2 than T3. Mazia, is it clear? Nabila, any doubt?
No doubt, sir.
Okay, just write it down. I'm giving you just 2-minute break. Then I will define you the last part of this chapter just in 5 minutes. Then we'll start thermodynamic. Okay.
Okay, sir.
Okay. You will have done till this part?
Yes, sir.
The last part of this chapter is Wien's displacement law. Suppose you have a rod, any metallic rod, which is put under flame to heat it to very high temperature. So in which color it will glow initially? Black, blue, green, or something else?
So it will become red first.
Okay, and on further heating?
So it will turn yellowish and then white and then it will turn blue, sir.
Okay. Every object which having temperature T, it will have some thermal energy according to the relation 3/2 kBT, where kB is any constant and T its absolute temperature. So energy will be proportional to its temperature. In second part, on having this much amount of temperature, it will radiate some electromagnetic radiation in the form of photon. So energy in that case, in terms of radiation, it will be hc by lambda, where h is Planck's constant, c is speed of light, and lambda is wavelength. You must have learned about it in chapter 2 in photoelectric effect, okay, in chemistry. So if you compare these two segments, you will get 3/2 kB T is equals to hc by lambda, means a hot body is radiating or emitting radiation of wavelength lambda. So on comparing, you will get this T is variable and this wavelength is variable. The rest of the whole term is constant, 3, 2, kB, h, and c. So from this part, we can say greater the temperature of body, it will radiate smaller wavelength of radiation. Is it clear?
Yes, sir.
Yes, sir.
So wavelength and temperature will be inversely proportional to one another. So the whole term is constant. So state on the basis of Wien's displacement law, the maximum wavelength of radiation emitted by hot body is inversely proportional to its absolute temperature. It means wavelength inversely proportional to temperature. So move this T to left side. So there will be some proportionality constant. So lambda maximum into temperature will give you some constant B, which is called Wien's displacement constant, which is numerically equals to 2.3 into 10 to the power minus 3 meter Kelvin. Let me define a graph related to this expression. Let's say this is wavelength versus temperature. So one of the radiation at some temperature will be this. The next will be this, and so on. So this is the peak value of wavelength. For some temperature this, for this part, at some other temperature this. So if this is wavelength lambda1, so this will be temperature T1. This is wavelength lambda2, so it will be T2. So lambda1 is for higher temperature, but lambda2 is for lower temperature. So we can say wavelength and temperature should be inversely proportional to each other. Mazia, is it clear? So in terms of visible region, we have Vibgyor. So red having maximum wavelength, violet having minimum wavelength. So all objects initially at low temperature tend to radiate in red color, and on further heating, its color of radiation will tend to go along this way to reach violet and finally becomes black. Is it clear? Krishna, any doubt?
So finally it will become into.
It will somehow tends to become white and further depend upon its own temperature or tendency of its absorbing tendency, like in the case of black body. So finally it will tend to become white.
Okay, sir.
Any doubt related to this part to any one of you?
No, sir.
Okay, just write it down. You all have done?
1 second, sir. Done, sir.